Hello, and welcome to the first PowerPoint presentation on energy fundamentals. In this presentation, we will go through the distinction between energy and power, and we will also look at several examples. So let's go ahead and get started. So this first slide here, this is a quote taken from the Energy Reader, and this quote clearly states that some grounding, a basic foundation in energy fundamentals, is a critical part of energy literacy. So we're beginning that process here with this presentation on power and energy. So first, let's just provide a short definition for each of these concepts. Energy is often referred to as the capacity for doing work, and then power is the rate at which work is performed. And so one way to think about this is if you've got a certain amount of energy, and the power, the rate of use, will dictate how long that energy will last. So for example, if you have a battery with a certain amount of stored energy, if you were to use, say, a 1,500 watt hair dryer, you would use that energy much more quickly than if you were, say, powering a 20 watt light bulb. So a certain amount of energy exists, the capacity to do work, and the rate at which we use that energy, the power, will determine how long that energy will last. So let's go ahead and look at a couple examples. So here we have a light bulb. Most appliances, including light bulbs, have what we call a power rating. In this case, we are looking at an 80 watt incandescent light bulb. So the length of time that we have this appliance on, or this light is turned on, will dictate how much energy is consumed. So an 80 watt light bulb left on for 1 hour would consume 80 watt hours of electricity or energy. So in this case, the power rating of the light bulb is 80 watts. It's the instantaneous amount of energy that would use once it's turned on. And if we leave that on for 1 hour, then the energy that would be consumed, the electricity, would be 80 watt hours. Another good example is to think about a vehicle, a car. Here, a Cadillac CTS has a fairly large engine. It's 556 horsepower, and we convert that into kilowatts. That would be 414, just to give us a relative sense. So that's a large engine. So the energy that would be consumed, so that's the power rating. At full throttle, this vehicle can deliver 556 horsepower of power directly to the wheels. And so the energy that is consumed occurs over time, and that is the gallons of gasoline. Let's say 100 miles would equal approximately 5 gallons of gasoline at 20 miles per gallon. And 1 gallon of gasoline has 114,000 BTUs, which is a British thermal unit. We'll get to that in a little bit. So that would equal a total of 570,000 BTUs, and this is equivalent to 167 kilowatt hours of energy. So again, the power rating of the vehicle is 556 horsepower, and the energy is the amount that would be used over a certain distance. In this case, 100 miles would be 5 gallons, which is equivalent to 167 kilowatt hours. So now take into contrast a 2015 Toyota Prius. This vehicle has a power rating of 134 horsepower, which is about 100 kilowatts. That same 100 miles would only require 2 gallons of gasoline, given that a hybrid Prius gets about 50 miles per gallon. So that's a total of 228,000 BTUs, or 67 kilowatt hours. So this gives us a sense of power and energy, and also this notion of efficiency. A hybrid is a more efficient vehicle. It's using less energy to deliver the same 100 miles of travel. So another typical device we have in our homes is a furnace. Furnaces are rated in BTUs per hour. That's the power rating of the unit. And oftentimes they're in the range of 100 to 80 BTUs per hour. And we can convert that, if we wanted to, into another power rating that many of us are familiar with, which is kilowatts. And that would result in a 29 to 23 kilowatt power system. So that's the power rating of the device. And all the devices we have in our homes, our computers, our blenders, our refrigerators, they all have this kW or watt rating oftentimes on the label. So the energy that's used in the home really depends on multiple factors. The outdoor temperature, the thermostat setting, and the shell efficiency. How efficient is the home? Are there air leaks? Is there inadequate insulation? All these things will factor in to determine the amount of energy that's used over time. And that furnace, again, has the capacity to deliver 100,000 or 80,000 BTUs per hour. So let's say a typical home would use about 850 gallons of heating oil during a typical heating season. 1 gallon of oil is equivalent to 138,000 BTUs, which is 117.3 million BTUs. So 850 gallons at 138,000 BTUs is equivalent to 117.3 MBTUs, which is million BTUs. And that's the total energy that would be used during a heating season. And we can convert that energy from BTUs into kilowatt hours, and the energy use would be 34,377 kilowatt hours. So you've noticed thus far from this presentation that there's distinction between the units that are used to indicate power and the units that are used to indicate energy. So a typical unit of power would be the watt, and that's in the SI system, the System International. It's almost the equivalent of the metric system versus the imperial system that we use, inches, feet, etc. So the SI is kind of the national standard for units of energy and power, and the fundamental unit of power in the SI system is the watt. And that is equivalent to 1 joule per second. And again, a joule is a unit of energy. So a watt is a power is a use, a rate of use. In this case, it's 1 joule per second. Now, the other system, the UK, the US, which is the imperial system, they use what they call the foot-pound per second. The foot-pound per second is the unit of power. It's a rate of use. And the foot-pound is a unit of energy. And it's the energy equivalent to raise 1 pound of something 1 foot into the air. And so we have here units of power, watts, and foot-pounds per second, units of energy, which are joules or foot-pounds. Another common energy unit in the imperial system is the BTU, which stands for the British Thermal Unit, and that is equivalent to the energy required to raise 1 pound of water 1 degree Fahrenheit. And so that's a measure of thermal energy, and the foot-pound, which is raising 1 pound 1 foot, really is a measure of work. Work meaning moving a mass a certain amount of distance. So energy is a very unique type of form of energy. Thermal heat is a very unique form of energy that has important properties and characteristics that we'll talk about throughout this course. So it's important that we're able to move from one unit of energy to another, and rather than having students do the mathematics for this, they can choose to if they want. It's actually quite simple. But there are these excellent tools that are available on the internet, and you can put in one energy unit and it will convert it to another energy unit. So I've provided to you here the links to those power conversion units and then energy conversion units. And so it's important that students are able to make these conversions, as I kind of did above, where I was comparing horsepower with kilowatts. And so it just helps us get a relative sense of these various forms of power and energy. Okay, so far we've talked about power and energy in the context of appliances, a light bulb, a vehicle, or a furnace. These concepts are also very important in the context of electrical generating systems. Okay, and so I want to look at here a couple examples. Coal-fired power plants are typically about 500 megawatts or larger, and so that would be equivalent to 500,000 kilowatts or 500 million watts. So when we look at a coal-fired power plant, again, about 500 megawatts or larger, the amount of energy that it produces is really a function of how long the system is operating. So if it's operating 24/7, 365, there are 8,760 hours in a year. So we would multiply that by the power rating, 500 megawatts, to determine the total megawatt hours. However, it is not typical for power plants to run all the time. They're oftentimes shut down depending on the need for electrical energy. Oftentimes they're shut down for maintenance and repair. So there's this term they use in the power industry. It's called the capacity factor, and it's really the ratio of the system's actual output, how much energy it delivered over a certain period of time, typically a month or a year, divided by the potential output. And this is this kind of unrealistic scenario that it was operating 24 hours a day, 7 days a week. So basically, it's analogous. This capacity factor is analogous to the amount of time a light bulb is turned on. Okay, in this case, it's the amount of time that the generator is producing electrical energy. So these units of power and energy, they're relevant for energy-consuming devices, such as light bulbs and furnaces, and they're also relevant to these systems that generate electrical energy. So let's do a little mathematical example. Let's say that we have a 500 megawatt coal-fired power plant. It's producing in 1 year 3,197,400 megawatt hours of energy. Right, megawatts is power rating and megawatt hours are energy. And so the formula to calculate the capacity factor is you divide the total energy produced times the nameplate capacity, 500 megawatts, times the number of hours in a year, 8,760. And this ratio gives us the capacity factor. In this case, it would be 73%. So this is an important concept in the power industry that's used to assess the productivity of various generating assets. Okay, so one more example. If we think about a wind turbine. So wind turbines have gotten much larger over the years. Now it's very common to have these 2.5 megawatt wind turbines. And history suggests, in terms of the experience running these wind turbine facilities, that they typically have about a 30% annual capacity factor. Okay, so this is a wind generator is much different than a coal plant. A coal plant, you can turn it on and off, although it takes several days or hours to get the coal plant up and running. Wind turbines are really subject to the availability of the wind resource. How often is the wind blowing? How strong is it? Will determine the amount of energy it produced. So if we have this notion of 30% capacity factor, we can calculate what we expect the annual production to be in a year. And this formula would be taking the nameplate capacity. In this case, it would be 2.5 megawatts times the hours in a year, 8,760, times the capacity factor. So in this case, it would be 6,570 megawatt hours of energy would be produced from a turbine with 2.5 megawatts of power rating at a 30% capacity factor. Okay, well with that, hopefully this has provided some clarity in terms of these two important energy concepts of power and energy. Power is a rate of energy use, and energy is the capacity to do work. Work can be understood by moving a mass, a physical amount of something from point A to point B. And energy is also, thermal energy is another important form of energy, which is also can be used to do work. And we think of heat energy as kind of the kinetic motion of the molecules in the substance. We'll get much deeper into energy, forms of energy in various conversion efficiencies, but for now we will conclude. So thank you so much.